This is a short video introducing our paper, Synchronizing Task Behavior, aligning multiple tasks during test time training. Our core question is, how can we leverage task variations across domain shift? In many real settings, we cannot train everything together, and tasks adapt independently at test time. This talk explains why that desynchronized behavior and how a synchronization signals based on source-run task relations can align tasks during test time training with minimal overhead. We will start from the problem, then show the method and result. Test time training updates the model while it is making prediction. It uses the current test input and the self-supervised task to compute a small training signal, then takes a few gradient steps online. Typical choice include rotation prediction, a masked feature reconstruction, or enforcing a simple invariance on features. This is different from test time adaptation. TTA often relies on batch statistics or consistency of prediction across augmentation, whereas TTT defines an explicit self-supervised objective and updates for a sample. The benefit is practically under strong distribution shift. We do not need robbers at test time, yet the model can still adapt its representation to the target domain as it runs. In multitask system, standard TTT treats every head or decoder as an errand. Each task adapts around, which leads to unsynchronized behavior and is matched prediction. A single auxiliary objective is usually not universal. It can have one task and leave another unchanged or even worse. This motivates task relationships modeling. If we bring in the relations run on the source domain, we can guide task time updates so tasks move together. The goal is simple: keep adaptation aligned across tasks and turn scattered improvements into consistent task gains. Our framework relies on two practical assumptions. First, the structure of task relations run at the source does not disappear after shift. It remains informative enough to guide adaptation. Second, if the task behavior synchronizer (TBS) is trained with a Schroeder masking ratio, it can predict task levels from masked task-specific returns with good accuracy. Under this condition, we obtain proposition 1. The target task loss is upper bounded by two terms, the masked prediction loss that TBS optimized and the discrepancy term to the full latent prediction. This gives a justification for using task relations as a synchronization signal during test time training. To check assumption 1, we compute task affinity metrics, how tasks relate to each other before and after adaptation, then measures the affinity gap. We observe a clear reduction after applying our synchronization, which indicates that the round mapping maintains the relative structure among tasks. We also test robustness under domain shift. Absolute task distance can change when the data distribution moves, but the synchronizer still shrinks the affinity gap reliably. This suggests that relationship signals we use is stable under moderate shift, supporting assumption 1 in practical scenarios. To evaluate assumption 2, we test the task behavior synchronizer (TBS) under partial visibility. Even when we mask up to 90% of task-specific latent tokens, the synchronizer retains at least 90% of its accuracy relative to full visibility. This suggests it can infer robbers from sparse queues, which is crucial for test time use. We also run a noise stress test with Gaussian perturbations on inputs. The synchronized TTT variant shows graceful degradation rather than collapse, which supports that the assumption holds over a practical range of distribution shift. Together, these results indicate that TBS provide a reliable supervision signal even when latents are heavily masked or input are noisy. At test time, an input image passed through the encoder to form a shared latent representation. We then project this into task-specific latents for each head. The main decoders output the task prediction as usual. In parallel, the task behavior synchronizer reads masked version of those task returns and predicts the levels. We add a simple objective. We minimize the difference between the TBS prediction and the main outputs. This gives a relationship-aware signal that a nudge or task to move together during adaptation. The effect is synchronized test style training that remains stable under shift and adds only a small overhead to the base model. We compare TTA, standard TTT, and our ST4 proposed S4T across multiple domain shift settings. In terms of task accuracy, S4T consistently comes out on top. Just as important, we look at synchronization metrics, step variance, dynamic time warping, and cosine similarity. With S4T, a step variance is lower, meaning tasks move more consistently toward adaptation. DTW, dynamic time warping distance, is lower, showing trajectories are better aligned. Cosine similarity is higher, indicating updates point in more similar directions. The takeaway is straightforward. Uh, S14 not only improves accuracy but also keeps tasks synchronized, which turns scattered per task gains into reliable overall multitask improvements under domain shift. We evaluate synchronization explicitly across domain shift scenarios. The comparison includes TTA, standard TTT, and our S4T. We use three metrics. Step variance measures how consistently tasks evolve during adaptation. Dynamic time warping compares the shape of task trajectory over steps. Cosine similarity measures the alignment of the update direction. Across benchmarks, S4T delivers lower SP, lower DTW, and higher cosine similarity. This indicates that tasks work together and remain well aligned during test time training, which translates into more reliable multitask accuracy under shift. On the step-by-step curves, S4T continues to gain accuracy as we allow more adaptation, whereas other TTT methods hit a short peak and then fall off. The difference comes from how we adapt. By using intertask relations to guide updates, S4T avoids overfitting each head in isolation and prevents trajectories from drifting apart. This matters in practice because test time budgets are uncertain. We may not know how many steps we can afford, and different tasks stabilize at different rates. S4T stays well behaved across a wide range of iteration counts, giving reliable improvements without fine-tuning the step budget per task. We tested the supervision source first. If we swap the task behavior synchronizer for a plain reconstruction head, the gains in TTT drop sharply. This indicates that level-focused mask prediction is the right signal for improving behavior at test time. Next, we vary the masking strategy. When every task receives the same mask region, TTT improvements in TTT performance is consistently highest. That pattern suggests the network is truly reasoning about the shared missing information across tasks instead of exploiting idiosyncratic cues. These two results explain why the synchronizer and the shared masking are central to S4T's stability and accuracy. We compare adaptation accuracy along with resource computational cost. S4T delivers top multitask accuracy while staying lightweight at 29 million parameters and about 0.37 seconds per inference. In contrast, TTT++ expands to 149 million parameters and 2.73 seconds, which is a large jump in memory and latency. Importantly, S4T sits in the same ballpark as the smallest baselines, roughly 24 million parameters and 0.13 to 0.30 seconds, yet it avoids their extreme trade-offs. In practice, S4T offers an efficient middle ground, high accuracy, synchronized adaptation, and deployable runtime. Thank you for listening. Full details are in the paper and code, and I have to take a question after the talk or by email.